and welcome. In this video, our goal is to find the Thevenin equivalent of this circuit when viewed through the terminals A and B. The first thing we want to do is that we want to find the value of the open circuit voltage of VTH. In order to do that, we have to know about the currents in the circuit, and an easy way of doing that in this circuit would be to use nodal analysis. Now we have 1, 2, and 3 essential nodes in this circuit. If we make this essential node our reference node, we have 1, 2, 3, all this is one node. So let's call this node 1, and this is node 2. Another thing you would notice is that this problem just got a lot more easier because there is a voltage source connected directly between node 1 and the reference node, and because of that, the value of the node voltage V1 would be the same thing as this the value of this voltage source. So it will say that V1 is equals to 30 volts. The next thing to do would be to move on to node 2 and write a KVL equation there. So say at node 2, N2. So we have this branch where V2 divided by 5. Then we have this branch where 3 amperes is leaving, so plus 3 times 10 raised to the power minus 3 milliamperes. Okay. Then we have this branch where we have V2 minus V1, which is in this case 30 volts, divided by 15 times 10 raised to the power 3. 15 times 10 raised to the power 3. Also, this is 5 times 10 raised to the power 3. And then we equate everything to 0 as we are writing a KCL equation. If we multiply through by 15 times 10 raised to the power 3, we would have it that 3V2, okay, plus 45, okay, plus V2 minus 30 equals 0. And with this, we say that 4V2 is equal to minus 15 volts. Then that would imply that V2 is equals to minus 3.75 volts. And that would mean that the current flowing in this branch is minus 3.75 volts divided by 5 times 10 raised to the power 3. So with that information, we can proceed to connect a virtual voltage source across these terminals, and that will be what VTH is. VTH, so it is connected across A and B. Okay, then we can write a KVL equation in this loop, and with that information we would have it that VTH is equals to 5 times 10 raised to the power 3 multiplied by V2, which is minus 3.75 divided by 5 times 10 raised to the power 3. Recall that this stands for the current flowing through this branch. That means that VTH is minus 3.75 volts. The next step would be to determine the value of RTH, which is the value of the resistance as when we measure through this direction with the independent current and voltage sources turned off. So RTH is what you get when you measure like that. Recall that turning off a current source leaves an open circuit, turning off a voltage source leaves a short circuit. If we proceed to turning off the voltage and current sources, we would have something like this. I would say it should be what you get when you measure with an ohmmeter here. So we notice that this is in parallel. This 10k resistor is in parallel with a short circuit. So we say that RTH equals 10k in parallel with 0. Okay, then these two resistors are in series with this, so plus 15k, then that would be in parallel with this 5k, in parallel with a 5k resistor. Any resistance in parallel with short circuit equals 0, so we expect to be left with 15 kilo ohms in parallel with 5 kilo ohms, and that leaves us with 15 times 5 divided by 15 plus 5, which is equal to 3.75 kilo ohms. Okay, go ahead to draw the Thevenin equivalent of this circuit using the information we have, and it will look something like this. Plus minus, we have 3.75 kilo ohms here, and we have minus 3.75 volts. We can redraw this and change over the direction of the polarity. With that, we would have the circuit to look more like this. We have the plus here and the minus here, then we can say 3.75 volts. We're just changing the direction of the flow of current. And that will be all for today. Thank you for watching. Don't forget to hit the like button and subscribe. See you next time. Bye.